started. So go ahead and get started. I will go ahead and reference the things that I sent out in an email. I sent out yesterday, just a few important things. So everything I'm saying right now is in this email sent out yesterday. So please read that to get an idea of what I'm talking about. Classes, of course, resumed today. So hopefully you all heard about that by now. Some of the repercussions of, well, it's not really a repercussion of the hurricane. I just went ahead and gave an extra day on quadratic equations in the quiz. I figured I would give an extra day on quadratics because in my lecture, I rushed through the end part. So the video that I provided in my math lab is a more detailed video that I gave my other section. I was able to get through all the problems. So if you go into, of course, lecture links, the lecture I have here is for my other section, which again, I covered all the problems in more detail. So that should be more helpful. And so that's due tomorrow instead of today. It was due tonight, now it's due tomorrow. And the quiz is pushed back Friday. Additionally, workbook 3, which I'm assigning, is due Friday. And it looks like a few problems. It's 2 problems per page, but the tutor, if you come to Friday's session, the tutor is going to work out every problem. So if you go to the Friday session, you could just watch him work them out, and then that's one less assignment you have to worry about. Definitely, you should have gotten your workbook by now. If you haven't, I'm still getting emails about where to find them. It's been a month. So again, University Bookstore, or you can get them online here from the bookstore website. I gave a link that goes directly to the book itself. And probably the most proactive thing you can do in this moment is take the advice. If you want to about the midterm, if you want to take the midterm remotely instead of in person, then you need to email me by Monday and just tell me you want to. And some of the factors that may go into this, I don't know, the midterm, if you take it through the proctoring service, it costs about $20. You take it during your usual class time. So that's when you will be taking the midterm during, regardless. If you take it in person, we're going to be taking it over in the library during the class time, but we don't have any lectures that week. So we will not be lecturing anything. It'll just be that whole week is reserved for the midterm. So that may be some factors that help you decide. Yeah, and Caitlin, midnight, that sounds fine. But yeah, that may be some of the factors. Now, if you think that you're just going to use ProctorU as a way to take the remote test and cheat, it's not going to work. ProctorU is, well, there's a lot of verification that ProctorU goes through. So if you're planning on using the website to cheat, you might want to ask a friend about how ProctorU works, and it might make you change your mind. If you took any math class, or you have a friend who took any of the math classes last semester, their experiences might be different than what you think of ProctorU. So I just want to give that heads up that if you think you're going to utilize it as a method of completely cheating, then ProctorU is it's a lot more elaborate than you think, and it's kind of clunky as well. So I'll kind of explain. Is the midterm multiple choice? No, it's not multiple choice. So that may be some things to keep in mind when considering whether you should take the midterm in person or remotely. Now, of course, if you have issues with the virus, then of course take it remotely. If you're trying to take it remotely just to, try to find a better environment to take the test or whatever, that's fine too. But it's not as simple to cheat on this test as you would think. I just want to make that clear, and just ask someone who's used ProctorU before if you're really that concerned about it. So besides for that, that was everything I sent out in my email. Again, the most proactive thing you can do is just email me and say you're interested in taking the test remotely. You could change your mind. This doesn't mean that you're locked in, but you know, if you let me know that, then I'm going to send you a follow-up email probably later on this week about directions on how to set that up. So again, read this. Again, it says that the midterm is going to be through the week of September 28th through October 2nd. So keep all of that in mind. Other than that, let's go ahead and pick up where we left off. So we are now moving on to radical equations, which is due Sunday. So we're going to be talking about radical equations today. And so radical equations, as I wrote up at the top here, just a fancy way of referring to equations that have square roots, or a root, a square root, a cube root, a quartic root, just any sort of radical symbol is the generalization here. So that notation would be square root. So some of the terminology it'll ask you about, the roots that you're taking is called the index. So if you're taking the square root, the index is 2. Or if you're taking the third root, the index would be 3, and so on. Everything under the square root, I've mentioned that terminology before, it's called the radicand. So that's just everything under the square root. And you can also rewrite, if you have a fraction as an exponent, that actually can be rewritten as a radical. We'll look at this later. But this is a conversion formula in essence. We'll be looking at that momentarily. So just to practice a few problems. Example 1 here, we could simplify. Go ahead and start off with the first 3, just to get an idea of how these work. So the square root of -8 squared. Now, the question here would be, well, you don't want to immediately jump the gun that the square root and the square cancel. Because really what's happening here is, since we have all these numbers, everything under the square roots, we want to evaluate that first. So -8 quantity squared is positive 64, and then positive 64 is just 8. And notice we don't have a plus or minus because we didn't apply the square root. The square root was already given to us. So notice that the answer is positive 8 as opposed to -8 if you would have canceled the square and the square root. So problem 2, sort of a similar idea. If you were to cancel out what we call fourth root or quartic root in the fourth power, then you would get -2, but that's not what we're trying to do here. Instead, what this problem alludes to since we have numbers, is the idea that we need to first simplify the -2 to the fourth power, which is positive 16. So that would be the fourth root of 16. And then the fourth root of 16, you can actually do this in your calculator. I'm not going to explain how to do it in the calculator, unless you want to know after class. So, or you're looking for a number such that what number, when you multiply to itself 4 times, would give you 16? The answer is 2. And that's why you get 2 here. 2 times 2 is 4, times another 2 is 8, times another 2 is 16. Again, roots in the calculator. Actually, now that I'm looking ahead, I'll go ahead and explain it right fast. So this is off of the calculator you're required to have. So with the fourth root in the calculator, a second, and then the caret symbol. The caret symbol is 1, 2, 3, 4, the fifth button on the first column. Actually, I already screwed it up. Sorry. There's one thing I forgot. Sorry about that. We're trying to take the fourth root, so we would put a 4 first, and then we put second and the caret symbol. And by pressing second and then the caret symbol, you're going to get a special square root. So 4, second, caret symbol. And then for those of you virtual, you should have this so far. And then 16. There's 16. You'll get to. So that's the calculator sequence. Now for number 3, it doesn't look like it would be a radical form, a radical expression, because there's no radical symbol. However, as I mentioned earlier, this can be rewritten as a radical using this conversion up here. And in fact, it will be helpful because it helps us visualize everything a little bit better. So it says whatever the denominator of the exponent is, that will now be the root. So this 2 is now the root. And then everything else, so the 64 and the 1 as an exponent, will follow as the radicand, everything under the square root. And then from here, you could take the square root of 64, which is obviously 8. And we'll look at a few more of those. So if that conversion didn't make sense, we have a few more coming up as well. In fact, number 4 here, kind of the same idea. The 16 raised to the 3/4. Well, we can go ahead and rewrite that as a radical because it is a number raised to a fraction, which normally means that this is a radical. It's not written in that way quite yet. So the 4 tells us the root. So it's the fourth root. The fourth root of what? This is 16 raised to, well, the third. That's how you do these. At least for these, this simplicity of form. So this is the fourth root of, well, what's 16 to the third power? We can figure that out right quick. And then using the same method from before, we can figure out the fourth root of 4,096. And you should get 8. Using that same calculator method that I alluded towards in problem 2. Problem 5, they sort of bump up the difficulty a little bit because now they have a negative sign as well. So now they have a negative 4/3 in the exponent. So now the question is, what do we do with the negative? Well, the negative in an exponent always tells us to flip the base. So the negative in the exponent would tell us that 216 would become 1/216. And now we got rid of the negative in the exponent. We apply the negative in the exponent by flipping the base. That's what it means in general. That's what the negative in the exponent means. So notice the negative sign is gone from the exponent because now we have applied it. We have flipped the base. And now the question is, well, how do we apply 4/3 to a fraction? Or in other words, well, really what we're doing here we're taking the third root of 1/216 to the 4th power. Because remember, that's how we rewrite. You might find issue with this if you try to jump the gun too quickly. If you try to do this in your calculator, the decimal is going to be way too great. So you have to simplify in between. So we're going to put some intermediate step here to help us. So when we have a fraction raised to an exponent, then both the numerator and the denominator both get their own 4/3. So we're basically giving the numerator its own exponent and the denominator its own exponent. So notice the numerator got a 4/3, the denominator got 1. So 1 raised to anything is just 1. 216 raised to the 4/3, that's the third root of 216 to the 4th. And what you should get is 1 divided by 1296. You would do 216 to the 4th power, which would give you a very large number, 2176, all of that stuff. And then you take the third root of that, using that method that I talked about in the calculator, how to take the third root of something. That's something you really need to make sure you can figure out on your calculator. And if not, you'll have to ask me, you can ask me after class. So we'll look at one more, problem 6 over here. And pretty much the same idea, we're taking the exponent of a fraction. So if anything, that means that we can give the numerator its own exponent and the denominator its own exponent, just like that. So the numerator got 1, the denominator got 1. And then we solved each one of those separately. So the numerator is the third root of negative 27 squared divided by the third root of 216 squared. Negative 27 squared is 729, and taking the third root of that. So for the numerator, you would get 9. So the third root of negative 27 squared, that should give you positive 9. The denominator, you should get 36. And 9 over 36 is just 1 over 4. So that's how you do types of problems like this. So if they give you the radical, you would just solve them. You solve them really using order of operations, everything under the square root, and then you work your way out. If it's not written as a radical form, then you must rewrite it as one. And then from there, you can simplify using the previous methods. So anyone have any questions about this before we move on to radical equations? Okay. So we'll move on to example 2 down here. So these are radical equations. Now there's variables. There's radical symbols, and there's equal signs. So naturally, we're going to go ahead and solve these, try to determine what the variable value is. So let's look at the first one here. So what the first one says is square root of 4x minus 8 is equal to 4. So the question is, well, now what do we do now that the variable is stuck underneath a radical symbol? Well, the first thought in your mind should be, well, we need to get rid of the radical symbol. You get rid of, well, a square root in this case. So I'll just rewrite it first. So how do you get rid of a square root? You would square both sides. So square root and the square both cancel. 4x minus 8 is equal to whatever 4 squared is, 16. And then from here, we can solve for x. So that's what we get. X is 6. There's also a caveat to all of this. And I mentioned it in the description right above all of these problems. If an equation has an even root, so a square root, a fourth root, all of that, please check your answers at the end. So if there is an even root that's given to you in the problem, you have to check your answers. If it's an odd root, like a third root or a fifth root or a seventh root, you don't have to check your answers. So here, if we were to check 6, then what we would do, because this is a square root, which means we would have to check. So that would be 4 times 6 is 24, minus 8 is 16, which is 4, which matches the 4 up here. So this does work. Now problem 2 is a little bit different because, well, there is a variable underneath the square root, just like before, but we do not want to square first because we have like terms. The -3 and the -12, they are like terms, and we want to, so ultimately what we want to do, before we start getting rid of the radical, any radical, so a square root in this case, we have to isolate the radical. That's what we have to do first. We have to isolate the radical. So that means by adding 3 on both sides, we are getting the radical expression by itself. So now the radical is by itself. The -3 is moved to the other side. Now, perhaps the more astute individual may notice that we could just stop right here. But perhaps nobody happens to see what the issue is yet. So let's say you were to just keep going with this problem. I'll come back to why one could determine that momentarily. So if you were to treat this like the previous problem, now we have the radical by itself, and we can go ahead and square both sides to get rid of these square roots. So if you were to square both sides, that would get rid of the square root over here. And -9 squared is positive 81. So what is that, 72? Should be 9. So you would get 9. So then we have to check it. Because this was a square root. So plugging t back in, that would end up giving us the square root of 81 minus 3. Square root of 81 is 9, and 9 minus 3 is 6. We get 6, but the problem over here said -12. So what that tells us is that we do not accept 9, and we say it's no solutions. So that happens sometimes. In fact, it happens fairly often. This is part of the reason why we need to check our answers. It's because we are subject to get extra solutions by rewriting the problem in a way that's more convenient for us. So, as I mentioned before, you could have noticed this earlier, and the place you would have noticed it at would have been when we were right here. So the question lies, well, what's the problem with this expression? And the issue is the square root will not produce a negative number. An even root will not output a negative. You cannot take the square root of anything and get a negative number. So that's why you would be able to see this and think, well, this can't happen. The square root, the fourth root, the sixth root, none of these will ever output a negative number. And if you don't see that, then you will end up finding out later on. If you could see this now, though, you don't have to check your answers. So that's kind of the versatility of going a step further with the understanding of all of this. Now, if it's an odd root, so a good way to think about it, even roots are picky. They're very picky about the numbers they can input and the numbers they output. Square roots, fourth roots, sixth roots, they like positive numbers generally. Odd roots, like the third root, fifth root, seventh root, they are not picky at all. They can deal with any number and they don't care. There's no restrictions with odd roots. This only applies to even roots. So in this problem, there's no solutions. There's no solutions. So does anyone have any questions about this? If not, we're going to do some more radical equation problems, starting with part 1 for example 3 here. Find the real solutions. So we move down to a third root. And so this one should be fairly reminiscent of the previous problem. We don't want to go ahead and get rid of the radical quite yet because we do not have the radical isolated. That root symbol is not by itself. The plus 5 is getting in the way. So we need to subtract 5 on both sides right quick. So 2 minus 5 is -3. And so from here, we're at a potential situation or a situation that potentially reflects the issue we had in the previous problem. We have a root by itself is equal to a negative number. And now the question is, can an odd root, a third root, can it output a negative number? And the answer is this is okay. So this is actually okay. So before, we could have stopped right here because we had a square root, and square roots cannot produce a negative number. Here, an odd root doesn't care. So in this case, you can take the third power of both sides. Third power to get rid of a third root. So that would give us 4x minus 7 now that the radical is gone. And now we have -3 to the third power, which would give us -27. Add 7 on both sides, we get -20, divide by 4 on both sides, and then we just get -5. And luckily for us, we do not have to check our answers. We only have to check answers if the root involved was even. But we had a third root, and 3 is an odd number, so we do not have to check our answers. This one's fine. The same manner, let's move on to problem 2. So here we have a fifth root, and the radical already seems isolated. So if anything, that makes things a little bit convenient. It's one less step we have to do. So we ask, well, can we have the fifth root of anything and get a negative number as a final answer? And this one is okay as well. This situation can happen. If this fifth root was a square root, then we get to stop the problem right now and say no solutions. The square roots cannot output a negative, but odd roots doesn't matter. So to get rid of a fifth root, you apply a fifth power. Fifth root and the fifth power cancel. And negative 2 to the fifth power, that's negative 32. And we get a quadratic, so something reminiscent to the previous section. And we put this into standard form, which means all the terms are on the same side and the exponents are in decreasing order, like we talked about in the previous section. And from here, well, we have a quadratic, so naturally we can factor. So let's see, multiplies together to give us 32, adds together to give us 18. 8 and 4, no. See, does anything work? 8 and 4 doesn't work. What about 16? 16 and 2. Cool. So 16 times 2 is 32. 16 plus 2 is positive 18. So this factorization would be good. And it's equal to 0. So that means that each part can be individually set equal to 0, like we did before. So then we get that x is negative 16 and negative 2. We do not have to check our answers here because we had an odd root to begin. And with odd roots, we do not have to check our answers at all. These are fine. So no need to check answers. They're going to be good by the virtue of having a fifth root in the beginning of the problem. So any questions up to here? Okay, so move on to example 3, part 3. So with part 3 here, the question is, all right, so what's the first step we've been doing with all these radical problems is, well, the first thing we like to do is to get the radical by itself. That seems to be the first step. And it turns out you can think about this either way. If you want to get the radical by itself, you would have to divide both sides by 4, not subtract. You'd have to divide both sides by 4. Now that's one way you can do this problem. It turns out, though, that you can, it turns out that the radical is technically already simplified. And you might think, well, what about the 4? Or the radical is already isolated. And you might think, well, what about that 4? That 4 does not make the radical isolated. And it's the fact that this is all one term. So this whole thing right here, this is one term. Remember, terms are separated by pluses and minuses. Now you could have divided by the 4, or, so what I had written down before was not wrong. It wasn't wrong. And you could have done it that way. But here, we can square both sides. But when we square both sides here, so x squared, we also have to square that 4 that's in the very front. So that's why I'm going to put a 16 here. And then over here, the square root and the square would cancel to give x minus 4. Or if you would have divided by 4 and square both sides, it would just be extra steps. It would have been the same problem, though, and you would have multiplied both sides by 16. So if you chose to divide by 4 and isolate the radical, that's perfectly fine. It would just be one extra step. But I'll look at this way, where we would distribute the 16. And we can put this in standard form. And then from here, it's just a matter of factoring. So that seems to be 8 and 8. Negative 8 times negative 8 is positive 64. And then their sum is negative 16. So then we get that x is 8, positive 8. So then the final issue we may have is checking the answers. We do have to check the answer here because we had a square root to start the problem. So naturally, we consider, all right, if we plug in 8 for x, will both sides agree with each other? And so we would have to check answers. So we would have 4 square root of 8 minus 4. 8 minus 4 is 4. Square root of that is 2. 2 times 4 is 8. So that would work. So this answer is good. Finally, for part 4, we have something that looks a little bit different. The reason why it looks different is because, well, there's no visible radical symbol. Well, that is okay because there is a radical. It's just not shown at the moment. So remember, 1/2 as an exponent, what that means is square root. It means the square root. So there is a radical in this problem. It's just not immediately evident. Because remember, the 2 in the denominator of the fraction and the exponent, that tells us the root. So that would be a square root of everything in the parentheses, of everything that is referring to. And so now it becomes a problem just like the previous sections. Now we have to get the radical by itself, which means subtracting 5. So we subtracted 5 on both sides to get the radical by itself. And from here, we can go ahead and get rid of the radical now that it is isolated. We square both sides to get rid of the square root. Notice I have the x minus 5 in parentheses as I square it. This means we will need to FOIL. So when we FOIL, that's first, outer, inner, last. Then we can combine like terms. The two minus 5x's become minus 10x. And now we combine more like terms by subtracting 3x on both sides and minus 3 on both sides to get this as a quadratic equal to 0 to prepare for factoring. That would be minus 3x and minus 3. So that's x squared minus 13x plus 22. And now we can factor. Negative 11 times negative 2 gives positive 22, and their sum is negative 13. So we get 11 from the first factor and positive 2 from the second one. Now, there's only one thing we have to consider now. This point of consideration is, do these numbers actually work or not? If we check the answers, will we end up getting a sufficient or satisfied equation? So what about if we have x is equal to 11? So if we plug in 11 into the original equation from the very, very beginning, that's 5 plus 3 times 11 is 13, plus 3 is 36 to the 1/2, which is the same thing as the square root. So then this will be 5 plus 6, which is 11, which is what it should be. So 11 works. But what about 2? We also found an answer of 2. The same thing, we plug in 2 into the x values. So that would be 3 times 2 plus 3 to the 1/2. So then that's 5 plus, well, 3 times 2 is 6, plus 3 is 9, the 1/2. And 9 to the 1/2 is the same thing as the square root of 3, or the square root of 9, which is 3. So then we get 8. But we were supposed to get x, which is 2, for that problem, because that's what we plugged in. So 2 is out. We reject 2. It's an extra solution. So 11 is the only answer here. So this tends to be the problem whenever we deal with even roots. This is a problem that sometimes occurs. Are there any questions here before we look at the next one? If not, we'll go ahead and look at the last one, which is I think it's a fairly tough one in this section. Find the real solutions of, and I'll go ahead and rewrite it over here. So what I like to do, or the way I would like to look at this, is I would rather look at this as radicals instead of fractions as exponents. So what that tells us, how to rewrite this, so this would tell us that we have the square root of x to the third minus 67, the square root of x to the first, which is just x. So I didn't do any algebra. I just converted these to their radical counterparts. And so the reason I did that is because with radicals, we have the first thing we tend to do is try to isolate the radical. But there's two radicals here. There's two of them. So what we need to do, well, we need to isolate both of them. I think, how do we do that? Well, by adding this term on both sides, we will do just exactly that. And now both radicals are simplified. And the 67 is still part of the same term of the square root of x. So this is still the same term. And from here, the reason why that's important is, well, what do we do after we isolate the radicals? We get rid of the radical symbol. In this case, it's a square root. So naturally, we square both sides. So that would just be x to the third is equal to 67 squared. 67 has to be squared here. That's how you get 4,489. And then square root and square cancel. So then we are left with x. And we're going to move the x term to the other side so we can have a quadratic, or not a quadratic, a polynomial in standard form. Get everything to the same side equal to 0. That'll help for factoring purposes. The reason why this is important more so is because both of these terms have an x in common. So we can factor out the common x. And by factoring, that means that we can break up both parts and set them individually equal to 0. Now, one of them is already solved for, and then the other one we have to do a little bit more work. Here we can add 4,489 to both sides, apply the square root to get x by itself, and we get plus or minus 67. Because that is the square root of 4,489. Finally, we have to consider the notion of checking our answers. And we do have to check our answers because we had an even root. We had square roots. So x is equal to 0. That one should be pretty easy because you just get 0 minus 0 is equal to 0 after you apply it. Everything zeroes out. So that one's easy. So if anything, x is equal to 0, that's going to be one of the answers. One of these that's really easy to knock out is negative 67. Negative 67 cannot be a solution. And the reason why is because when you try to take the square root of negative 67, such as in this term right up here, if you try to plug in negative 67, the calculator won't even give you an answer. It'll just say undefined. So if you can't even get an answer through the calculator for plugging that in, then it's an extra solution and you can toss it. And it turns out positive 67 will work. So you get two answers. X is 0 and 67. Does anyone have any questions up to this point? You use the plus or minus to answer your question. You use the plus or minus whenever you apply the square roots, whenever you apply the square root to both sides of an equal sign. So that's whenever plus or minus comes into play. So we haven't used it before for the other problems because converting from a number with a fraction exponent to a radical, that doesn't mean we're applying a radical symbol to both sides of an equation. So only upon this arithmetic step do we apply it.
Square root property.
Square root property, yes. Yes, square root property. Yeah, so another, that's a good point. So another derivation of this, talked about it here. Yeah, square root method thing. So that's another point of derivation.
And it only applies to square roots. It doesn't apply to third roots, fifth roots, all that. Just
Only the even roots.
so it does apply to like a fourth root as well.
It doesn't really come up in this class. So it does apply to fourth root as well and sixth root and eighth root, the plus or minus thing, but we don't really use it much in this class.
Thank you.
Yep. So I wanted to at least look at the first one or two problems from the next section as well. So this concludes everything for radical equations. This is pretty much the process. So for this last section, it's isolate the radical, get rid of the radical, and solve as normal, and potentially check your answers. That's pretty much the summary of this whole section right here of what looks like just a mess of scratch work. So that's what all this comes down to. So there's also something called equations of the quadratic type, which might or might not be a section you enjoy due to some of its ambiguity. And I'll try to explain the pattern here a bit today, and we'll talk about it more so next week. So equations of the quadratic type, if you've taken this class or a class like this before, you will know of this section as the substitution method section. And what we're doing is we have forms that look like quadratics. they have this very close feel to them, but they're not quite quadratics. And I'll explain what this means in a bit. But if we apply some sort of quick substitution, then what we do have is, after we apply the substitution, we will have a quadratic. We can solve the quadratic and then use the substitution to ultimately fill in that remaining gap for us. So, for example, 1 here, it looks really close. It's not a quadratic, because a quadratic would be x squared minus 29x plus 100. So this is not a quadratic, but it's formed like a quadratic. So wouldn't it be great if this instead was x squared and this instead was minus 29x, and then that stayed as 100, then that would be a quadratic. Well, it turns out we can utilize this structure by using something called, well, ideally it's called U substitution. It's a U substitution. We use the variable U as this placeholder variable. And it wants us to determine, how do we replace x's with u? So how all of these will start off, you have this variable u that's going to take the place of x, but we need to establish a rule. How does u take the place of x? What does u have to take the form of in order for this to be a quadratic equation? And in this problem, so really what I want to find, so if this was x squared minus 29x plus 100, then it seems like we would want the x squared here to become an x. So really, that middle term tells us that we would want u to be x squared. And the reason why is if we take that original form up here, well, every place I see x squared, I'm going to put a u. And I'll ignore the x to the fourth for now. So instead of x squared, I said x squared is now u. So I'm just going to put a u. There's a plus 100, there's an equals 0. And then now there's this part as well. So we either have to have all x's or all u's. We can't just have it mix and matched, or else you're not going to be able to solve the problem. So you might think, well, all right, we have u is equal to x squared. How do we take care of x to the fourth? We actually already did, because x to the fourth is x squared squared. So this is just fundamental algebra here. So it turns out that we already, well, ultimately, x squared is u. And you'll be finding this process repeats fairly often, that the first term is u squared, no matter how complicated it looks. So chances are that's going to be u squared, and the next one, that's going to be u squared. This tends to be a fairly repetitious process. But in other words, we can go ahead and complete this down here by writing u squared. So we do have a representation for it. And this is by applying this rule up here, this very important rule that we will come back to, and then making the substitutions as appropriate. So now we can treat something that looked like a quadratic, now we can treat it as a quadratic, which means all we have to do is factor. So let's see, 25 and 4. So here we get that u is 25 and u is 4. But We are not done. A lot of people like to just stop here. Just because we finished a sequence of steps doesn't mean that the problem is over. U is just a placeholder variable, which means if you try to put in these answers into MyMathLab, it's going to say you're wrong every time. We don't want U, we want X. U is just a helpful placeholder. So now what we have to do is go back to our rule. The rule tells us that U is equal to X squared. So we found two values of U. One of the U values we found was 25. So instead of U is equal to X squared, it's now 25 is equal to X squared. And one of the other values we found was 4. So 25 was equal to X squared. And the other value we found was 4 is equal to X squared. Because we found two values of U. So we plug in those values into U, and it gives us two separate problems. And from here, because it's two separate problems, we can go ahead and solve for X in both cases. So here we would take the square roots, which would be plus or minus. And then same thing over here. And the square root of 4 is 2. So we actually have 4 answers to this problem. It's 5, -5, 2, and -2. Does anyone have any questions so far? If not, we'll go ahead and do the next one and we'll call it a day. So next one, it's quadratic in type, but it's not a quadratic because ideally, if it were quadratic, we would love for that to be X squared. And then we would love for this to be 63X and then minus 64. That would be great. But that association alludes towards the U substitution itself. So the middle term, as I mentioned, the middle term normally gives us an idea of what U should be. It's X to the third. Not with the 63. It's just X to the third. We want the number to remain after we apply the substitution. The middle term normally gives us a good intuition about what the substitution should be. And naturally, that will end up applying to the next term in the way you would expect to make that larger term an X squared. And this makes sense because if we're trying to replace X to the 6, well, that's X to the third quantity squared. So again, some fundamental algebra, and we just said that X to the third is U. So that's sort of the justification. So now we have U squared plus 63U minus 64 is equal to 0. And now we can utilize this quadratic form. And in particular, we can factor. So I see plus 64 and minus 1, which would give us negative 64 and positive 1. So we factor and we find these u values, but u's are only a placeholder. We do not want u values. We now want to convert to x values. So what we need to do is bring our rule back. So we bring our rule back. And so we had two x values that we found. Negative 64 is equal to x to the third, and 1 is equal to x to the third. That's the two x values we found. And from here, all we have to do is get x by itself in both cases. So to get x by itself, when it has a 3 on it, we have to take a third root, which does not have a plus or minus component. And same thing with this problem over here. So the third root of negative 64, so you can do that in your calculator. You get negative 4. And the third root of 1 is just 1. These would be your final answers. And up to here, we will call that a day. So if you don't have any questions, you are good to go. Otherwise, I'll stick around for any questions you may have.